So let me dive into it. I'm Rick Goldstein. Nice to meet everyone. For my hackathon project, I worked on something called embedding and transformer synthesis. For this project, I took a binary classification function. I'll show the picture of that in a minute. And I use this binary classification function to extract some embeddings based on the function, and ultimately use these embeddings to create a working one-layer transformer that recreates the original classification function. So why would we do this? Why do we care? Well, there are a lot of models running in the wild right now, including ChatGPT and GPT-4. No one really knows how these work. If we could either replace these models or replace small components of these models with pieces that we fully understand because they were written by humans, then we can have more confidence that the models will work how we want them to work. We will not engage in unsafe or otherwise deceptive behaviors. So this is a little abstract. Let me dive into what I actually did for the project. Can you all see the new screen that I just pulled up?
Yes.
Awesome. Cool. So a few months ago, an alignment researcher at MIT, Stephen Casper, posted a few challenge problems. For one of these challenge problems, he created a binary labeling function. Here is the function in Python. Here is an image of the function. And he trained a transformer on this function. The transformer is a little bit noisy. So it doesn't fully recreate the function, but it recreates most of the function. And he asked researchers, what are the weights of the transformer actually doing? How is this transformer actually working? So I've been digging into this question on this as a research area for the last few weeks. And I have a hypothesis for what the transformer might be doing. But for today's hackathon project, or for this week's hackathon project, I want to take my hypothesis of what the transformer is actually doing and see if it is a cohesive hypothesis. See if I can actually take my hypothesis and recreate the initial labeling function, or to see if there are any components that I might be missing. So for the project, I want to try to recreate the transformer weights and a set of embeddings that can, when combined, can create this function. So how did I do this? The first thing to know about this function is that there are a few inequalities that help dictate part of the shape of this function. So we have lesson inequality here that corresponds to right here, where you can kind of see jumping back and forth between black and white. It might be black on one side, white on the other, and vice versa. You can see a second inequality here, which manifests itself here in the function. And again, you can see jumping between black and white. Then you can see a third inequality, which turns out to be a line here. And again, you can see jumping between black and white along the function. So I use these three insights to create a set of embeddings that somewhat match what I just showed. Sorry, give me 1 second to find it. Okay, so it's right here. So you can see I create a set of embeddings based on the line when the line switches from true to when the function switches from true to false, from red to blue, based on the line. So this is one of the three inequalities, and then likewise for the other two inequalities, I created a set of embeddings where that switches from blue to red and red to blue based on the second function, the second inequality, and then likewise for the third inequality. So these all take the same shapes, and then based on qualities of where the overall labeling function is switching from true to false or false to true, that's what dictates these shapes, these rows. And these rows are only set if there is in fact a change along that point along the function. And then I created a fourth set of embeddings based on whether for lines that are fully blue, fully false, as well as lines that are fully true, fully red. So I built turns out being 27 embeddings, 26 for the x dimension and 1 for the y dimension, and I can combine all these embeddings to recreate the initial function that we started with, the initial labeling function. I have more details about the exact math I used to combine this, to recreate this in my write-up as well as the code. But the overall gist is take the initial functions, the initial inequalities, generate a bunch of embeddings, and then combine them to create this overall function. Once I have that overall function, I can then synthesize a transformer. So the transformer has a bunch of parameters that we all know. I can set the embeddings based on what we just discussed. And then I can cleverly set the rest of the parameters of the transformer. And by setting these parameters, I can then, again, recreate the same function. So just to pause, so what we've done so far is we took an initial labeling function. We found the core functions that are dictating behavior for this labeling function. We use those to create a set of embeddings, and then we combine those embeddings into a transformer to recreate the initial function. So again, like, why do we care? What do we want to do with this? So I can use this to examine my initial hypothesis. So I had some ideas about how the transformer might have initially worked. The initial transformer has a bunch of points that are off, that are somewhat weird, that don't quite fit. I can modify one of the embeddings in my initial transformer. So I modify one of the y embedding, and I can see some behaviors that are similar with how this is wrong along this curve here, and then some spots in the trained transformer that don't quite match my modified model. So I can be like, maybe my hypothesis is somewhat right, but there's some areas that I haven't fully explained yet. And we can imagine going forward in the future, we could synthesize a few synthetic transformers based on different hypotheses and see which of those are most similar to the transformer that we've been trained to help us understand or interpret what our trained models are actually doing. So I have about a minute left. Let me wrap up. What are the next steps? What do I want to do with this? So I've trained this on a relatively simple classification function. I would love to move to larger functions, to move to language models. So I'm going to begin in a few. So once I write this work up and clarify a few things, the plan in about a month or so is to move on to tiny stories, which are small language models that can reproduce like elementary school level stories, and try to look for patterns in these small language models, and then to see if I can artificially synthesize small language models that can create small, simple stories. And yeah, that's my project. I'm happy to take any questions. Thank you.
Nice. All right. Any projects or any questions are welcome. Any projects as well, of course. But I think that's over for now. Any questions are welcome. Maybe I can start out. So I'm curious. You say tiny stories. Which sort of patterns are you imagining you might see? So this is of course like a binary masking pattern. If you think tiny stories and language models, that's some different ones.
Oh gosh, I don't know. That's a really good question, and I'm not sure. But I think I'd like to start out with like parts of speech, see how the language model predicts from noun to verb, verb to, I don't know, preposition or whatever. See if I can detect things like that. I guess that's part one, and then two, I'm not fully aware of how tiny stories tokenizes words, but if it uses subword tokens, see if there's a pattern from first portion of the word, second portion of the word. But I think like at a high level answer is like, I don't know yet. I need to dig in and spend some time interpreting these models before I know what it is I'll want to try to recreate in Handcraft.
Nice, perfect. Any other questions? All right, how do you imagine this? Oh yeah, go ahead. If there was anything. All right, yeah, I'm curious. How do you take this on like from an AI safety perspective? So this of course like increases our understanding of the models. How do you think about it when you work on a project like this into something like the broad scale conceptual AI safety?
Yeah, well, I think the dream is, I think we're like very far away from this. Is instead of having to use training data and having to use backprop to create a model we don't really understand, it would be amazing if we could handcraft all the parameters for a massive transformer. I think like we're very far away from that because I don't know how GPT-4 has what 30 plus transformer layers, and what I built today has one. I think there's a ways to go. But I think we could figure out what are the core 10 things, 20 things that GPT-4 is doing. We have the potential to build a much more interpretable model. And some of the concerns about a model doing things we don't want it to be doing, we might be able to remedy or partially remedy if we can understand how the models working, because we coded it up ourselves using human logic, human intuition. Again, like whether or not this is possible and like how far we can actually go, like, I don't know, but that's the intention. I want to explore it and see how far I can get with a small model before I make any claims about whether or not it's possible for large models.
Yeah, perfect. And then there is someone whose mic doesn't work, but they ask, would you say handcraft using presets, like how genes preset code for neurons? I assume this is sort of like, okay, do you want to have some sort of modules for the transformer, some 40 functional modules to recreate GPT-4 from, or something like this?
I think so. I don't understand how genes work at all, so I'm not quite sure I fully understand the question. But yeah, I think what I did for this project was I found one pattern that I then recreated with these set of embeddings. I can imagine finding 10 or 20 such patterns and trying to recreate them all and try to get them all working together for a larger handcrafted transformer.
Nice. Very interesting. All right. I think we will jump straight on to the third or the second spot project, which is who cares about brackets. So thank you very much to Rick. We can give him another little applause. And there are some muted faces also giving applause, I think. That's perfect. All right, do we have anyone from who cares about brackets in the room?
Yes, that's me. Hang on, I'll just share my screen. Can you hear me okay?
Yes, that is perfect.
Cool. Okay. Can you see that screen?
Yes,
presentation
so we
screen?
see the Discord screen at the moment.
Oh, you see the Discord. Oh, that's not great. Hang on. Let me try and share the. Why is that not working? Hang on. Let me just. Maybe if I just minimize this and then.
I think you can click the second tab called Screens instead of Applications when you share your screen as well.
Potentially that's it. Okay, I think here we go. Yeah, that should work. And then, yeah, if we just click and start. There we go. You can see that when it's full screen, yeah.
So we can actually see the full screen.
Oh, okay. Let's just go through like that then.
All right.
Yeah. So yeah, that will have to do. Okay, cool. So yeah, we were kind of interested in how conceptual information is passed between positions in sort of large language models. In our case, GPT-2 small, that we looked at using Transformer Lens. And just sort of concretely, what I mean by that is a sentence such as the following. Yeah, we chose to look at sort of brackets as a nice example of this. So if you take the following sentence, John and Mary went home with a bottle of milk, which sort of makes sense with or without the open bracket. In the first case, the next token is predicted as a closed bracket with a very high probability. Whereas when you replace that open bracket with a space, the likelihood of this vanishes to almost zero. Now that's not all that surprising. GPT-2 is, of course, pretty good. You would expect it to be good at this task, but the question is why and how? How is it able to get that information from the open bracket position to the closed bracket position and make that accurate prediction? So we sort of had a number of different ways of approaching this. Our initial hypothesis was that each subsequent token, subsequent from the open bracket, would likely kind of attend strongly to that open bracket position until a closed bracket is reached, and then we might expect it to not attend so strongly. And so we went looking for this, and we sort of averaged the attention paid by the sort of green tokens to the open bracket, and then subtracted that from the attention paid from the red tokens. And we ablated that across layers and heads, and sort of identified what we thought were a couple of likely candidates using sort of randomly generated sequences and real sentences. And that sort of looked promising, but we found in a few other sort of studies, or in a few other experiments that we ran, that direct attention is not necessary for this task at all. And so the way to read this graph is if you take the sort of source token on the bottom, so I think the open bracket is the one we're predominantly interested in here, and you sort of patch the attention from the final token, from the final position to this open bracket position, so that the final position cannot attend directly to that open bracket. It is still able to correctly predict the closed bracket token. You can see the probability decreases slightly, but it's still able to make an accurate prediction. And if you prevent all of the subsequent tokens from attending to that open bracket, then that probability drops right off to approximately zero. So we can see from this that the information surrounding the open bracket is being passed is clearly able to be passed through subsequent tokens. And although it may be the case that it is able to get that information directly, and that's something that I sort of didn't look into much more than what you see in front of us, we can see that it's definitely not necessary, and it is able to get that information via other tokens, which we thought was pretty interesting. And we tried to investigate this further by sort of having a sort of cutoff layer and a cutoff token, and sort of gradually patching more and more layers and tokens. And we saw a sort of fairly gradual drop off in both directions, sort of indicating that there's not really a sort of clear layer through which this information is passed or anything like that. This is not very fine-grained, and something I sort of want to talk about at the end about how we can go about this in a better way. And I have some ideas, but I also feel like this sort of tooling for this is potentially slightly limited at the moment, and it would be great to sort of think about that more. But yeah, that was sort of one approach that we tried, and because we weren't getting very far with that, we then sort of investigated short sequences. So for example, if the next, so for example, a string like this on the right, we have an open bracket, a token, then a closed bracket. So essentially you only need to attend to the previous position. So there's so direct attention is the only option here. Excuse me. And again, this was more interesting in the sense that we isolated the fact that if you patch the first 2 or 3 layers, then the model struggles to predict. So we sort of saw that the first few layers were sort of very important, and we identified a couple of heads, or combinations of heads rather. So one head from layer 2 combined with another head from layer 1, which seemed to be very much responsible for this. But at the same time, it didn't stand up to scrutiny. And we patched with different tokens that yielded different results. And we tried with different kinds of brackets that yielded different results. So lots of sort of dead ends really, but approaching it from lots of different angles. And again, just to kind of finish off on kind of the different approaches we took, we tried averaging activations across similar sentences, so taking a whole bunch of sentences with the same structure and the open bracket in the same position, creating an average set of activations, and sort of exploring sort of close-end similarity, and then the activation patching experiments again, hoping that it would sort of remove noise and improve generalizability. But again, the sort of the patterns we got out were sort of very mixed, didn't correlate very well, and we were sort of left with the conclusion that there was no such circuit. Now, this sort of raises 2 types of questions. Either we don't have the right tools, or there are sort of other experiments that we need to run in order to decipher this. And I think there are lots of interesting sort of ideas surrounding that about how we could better investigate this. And I have a few ideas and a few experiments that I want to run. But then it also raises questions about whether circuits are a good way to model all sort of, I guess, conceptual sort of ideas within a model, and whether that actually represents a good way to do that. And although there's been a lot of success with that in some instances, maybe for other sort of cases, that's not appropriate. So I'm sort of interested in those ideas as well. So yeah, I'll probably sort of finish there, but happy to take some questions. I don't really know how much time I have left, but yeah.
Nice. You're definitely within time. Just another minute left or so. But thank you so much, and a little applause. Thank you. All right. Any questions are very welcome. So we have someone in chat asking, when you tried different types of brackets, were there any common patterns for curly brackets, square brackets, or none at all?
Yeah. So yeah, just going back to this sort of diagram here, which was sort of where we were looking at that. So again, we saw with square brackets, we saw that rather than the first sort of 3 layers being important, it was the first 4 layers. But then we ablated that to sort of look at which heads might be responsible, and there were no clear patterns there, and the same pairs of heads definitely didn't show up. So there didn't seem to be any correlation there. And we tried with sort of angular brackets and curly braces, and again, different patterns each time. But we did find it interesting that in this case, it did seem to correlate with sort of early parts in the network. And whereas we didn't really see that with some of the other investigations we did. So for example, here, there wasn't, it wasn't like after the first sort of 3 or 4 layers of cutting those off, then suddenly the performance sort of increased rapidly. And here we didn't see the sort of early layers being particularly important. So we also sort of wondered whether this was representative of the right task. I mean, to me, open bracket, letter, closed bracket looks more like a list, rather sort of like a sort of list item, more than sort of a phrase within a pair of brackets. So Yeah, again, this simplified the problem because you're only dealing with sort of direct attention, but yeah, whether or not it represents the true task is an open question, I think.
Yeah, fascinating. Did you try as well with something like JavaScript or something where parentheses, or for example sentences where the brackets actually mean something more substantial than in the test examples you showed?
No, we didn't. We did actually think about code as being a very obvious example where sort of brackets were important. And we didn't really have time, but we started to think about sort of nesting brackets as well. But given that we didn't really understand single brackets, it seemed like not the most sensible idea. Yeah, I think trying with code examples would be an interesting line of research to continue with. But no, we didn't try that.
Yeah, I think there was another a previous hackathon project that I think did the nested brackets, but in a very simple model where the only thing it did was brackets and then figuring out, okay, how does it figure out the how many closing brackets are left, like which level of the of depth it is in. Yeah, maybe I can find that later. And then last question in the chat is, which type of ablation did you use?
In terms of, is there one in particular talking about? So I'm not sure what that refers to. As in, well, when I say ablate, I mean sort of taking. So for example, let me find it. So yeah, so the one in front of us. So by that I mean identifying. So when we've identified here which two layers seem to be responsible, then trying to find out which heads within those layers are responsible. That's sort of what I'm referring to by ablations. So yeah, sorry, maybe not in the way you're intending. Does that answer the question? Or maybe it's something else you meant.
I think so. Rick put something down as well with zero ablation or mean ablation. Yeah, but in the chat, they're probably thinking of a different type of ablation.
Yeah, maybe ablation wasn't the right term to use in that context, but yeah, essentially just trying to sort of understand which parts of each layer might be responsible for that. So I think you can see here that we identified. So you can see that when you sort of patch layer 1 and layer 2 together, and layer 0 and layer 2 together, that's when you get the biggest drop off in terms of accurately being able to predict a closing bracket. And then when we sort of looked at the heads within the head combinations within those two layers, you can see that it's sort of concentrated within a couple of examples. But again, this didn't really sort of stand up to scrutiny. But yeah, it was interesting.
Nice.
So that's what we did.
Yeah, and it's just last question from me before we jump on to the fourth spot. What are the next experiments you're thinking of, and like how do you think, like, do you have any hypothesis for why this circuits thinking didn't work out, or
yeah, so yeah, definitely some things I want to try. So just going back to this, I mean, clearly you can see there's a couple of heads here which seem to be important, and I'd like to know that even if the model is able to sort of communicate indirectly through layers and through other sort of positions rather, whether this is sufficient, and if you sort of prevent intermediate tokens from attending directly back, whether or not it can still do this task through direct attention. I suspect it can, but we didn't check that. I'd like to check that. And then I feel like with this is quite a coarse measure, and I would like to kind of break this down a lot more and sort of block sort of intermediate sort of positions from attending directly to a possession before that. So I think there's a lot we can do to sort of break this down and try and understand more about what's going on there. Yeah, essentially, I just want to dig a lot deeper and try to understand this rather than, I guess, looking at code examples would be interesting. There are lots of interesting things to do to sort of explore once this is understood. But my kind of main thinking is to sort of really sort of dig deeper on this and see if there is something to be understood here. And if there really isn't, then I think that starts to open up some very interesting questions about, are circuits the right way to sort of understand this stuff of behavior? But yeah, unknown so far.
Yeah, awesome. I think it's these sorts of projects that, poke holes at things, and then suddenly you have different methods or different perspectives. So excited for the future work there. Thank you so much. And let us jump on to Victor and Ave with the project where they are training, interpreting, planning.
Let me share my screen.
Yes, we can see your screen. Backtracking transforms.
Yep. So yeah, our project was backtracking in transformers with myself and Victor. So basically, a huge concern in the alignment community is inner alignment. And the main goal of inner alignment is to ensure that the model we train is optimizing for the same goals that we set in the base objective. So the concern is that models might form internal search mechanisms or internal optimizers, which we can call MESA optimizers, that are different from the base optimizer. The base optimizer would be like Adam W or whatever, and then the MESA optimizer would be the optimizer within the neural network that's actually achieving the objectives that we're training the neural network to achieve. And we want to find the mechanisms that might form MESA optimizers and transformers, which are the architecture that's used for large language models. And we train our transformers on the task of finding the shortest path between two nodes in a graph or traversing trees. And we find that these models do learn planning and search. And in fact, they learn a form of backtracking where they are using their attention heads to attend to the goal and then iteratively attend to the nodes one away from the goal and then the nodes 1, 2 away from the goal. So this can be thought of as a form of backtracking from the goal to like the current state. And we basically prove this or have show some evidence for this using a combination of attention visualizations and activation patching. So we train our models on two types of graphs. The first type is fully connected graphs. So in this case, both of these types of graphs have 16 nodes in them. And in the first case, fully connected graphs, there is a path from every single node to every other node. And then in the second case, which is trees, there's fewer edges, and it's only one path from like every node to every other node. Or I mean, from the root to every node, and then there isn't a path from like every node to every other node. In this case, we mostly just try to get the model to predict the path from the root node to one of the leaves, which we specify as the goal. And a sort of confusion we have is like what even is planning. Many things can be thought of as planning, and like I guess the model might be computing, or when like you ask the model to recite a Bible verse, it might be retrieving information that it's going to say in 5 tokens. But like, is that really planning? Or I mean, if it's just like memorized somewhere. So we instead operationalize planning as any mechanism involving an iterative procedure to decide which action to take in order to achieve a certain goal. And ideally, this mechanism would be general purpose or retargetable, such that the model applies this for optimizing for a variety of different goals. And we find that our backtracking algorithm sort of meets this definition of planning. So the architecture of the transformers we train, they're all 6 layers, and they're decoder only. And they have MLPs, so they're not attention only. And we train 2 models, one on the trees and then one on the fully connected graphs. The one we train on the trees has 1 head, and then the one we train on the fully connected graphs has 4 heads. They both achieve really high accuracy. For the trees, I think it's like 99.99% on the test set, and then for the fully connected graphs, it's maybe like 99.3%. So here are the attention patterns for the transformer we trained on trees. You might not be seeing much, but like the interesting part are these like vertical lines. So this is the 0th layer's attention head, and you can see that first off, the way that the model is actually trained is it is conditioned on these edge list. So we convert the graph into like a list of edges, and we feed it to the model. And then we give it a goal. In this case, if you can see, the goal is actually to reach node 4. And then we give the model a starting node, which is 8. And then the model now needs to output a path from node 8 to node 4. This is basically the graph that we are using for this example. And you can see that in the parts where the model has to output the next step in the path, it's actually first attending to the goal. So we believe that this is likely just copying the goal into each of the other positions from which it can next do the backtracking. And then in the next step, we can see that the model attends to the edge where 4 is the outgoing node. So it's basically attending to all of the positions are tending to this edge. And then in the next layer, you see that it's attending to the edge 3 goes to 0, which is the edge right before that. And then in the next layer, it's attending to 1 goes to 3, or the edge 1 goes to 3, which is the edge 3 before this. And then the pattern sort of breaks, where it actually starts attending to multiple edges at once that are multiple steps away, which is a mechanism which uses some mechanism we don't fully understand yet. So it's clear that like the model can backtrack more than one step at a time. And then in the final layer, I'm guessing the attention patterns look much more uniform. So I'm guessing it's looking over all the edge to find some certain pattern using its MLP layer or something like that. And we also find that the model does know when it like finishes backtracking or when it's reached the goal in its backtracking, because we can see that in the first layer's attention head, the position for the goal actually does not attend to the edge, but rather it attends to some position at the end. And then in the second layer, that becomes the same thing occurs for the last 2 positions. And then for the third layer, the same thing happens for the last 3 positions, and then for the next layer, it happens for like the last 5 positions. So this probably means that the model is checking whether the last step of the backtracking actually reached the goal, and if it does, then it stops backtracking. It terminates its backtracking, and it just attends to the final position. So instead of just looking at the attention visualizations, we also do some activation patching, and we basically take this graph where the goal is to reach 4 from node 8, and then we also create a corrupted graph where we ask the model to reach node 11 from node 8, and then we look at the difference in the logits at position 0. So how does the model decide whether to go to 4 or to 11? And we find that the things that actually cause a logit difference is patching in at the goal position in the first layer, which is right before the model actually moves information about the goal to the position where it's to the actual position where it's predicting which action to take at node 0. So patching it in here actually just changes the goal, and this just completely changes the logits. But then from that point onwards, the only sort of position that really affects the output is like patching in at the position of node 0, which is basically just interfering with its backtracking process and substituting its backtracking from the corrupted residual streams like backtracking process. And this just completely messes up the output. So I mean, this basically provides some evidence for our hypothesis of how it's doing backtracking, because it's doing backtracking within just that position, except for the 0th layer where it actually moves the goal. And we also try another activation patching example where we create 2 slightly different graphs, where one graph is just like basically a line from 0 to 15, and then the other one is a line from 0 to 15, except the node 1 is and the node 2 are both children of node 0. So basically, this experiment was to see like how it used information about the edges to inform its backtracking. And we find that this one sort of confirms that there's actually like a separate backtracking procedure happening also along the edge positions, like over here. So it's not just backtracking from like which we call the shortest path positions. It's also backtracking amongst the edges at the same time, I guess, to speed up the process. But this information, which is also happening simultaneously, doesn't really affect the actual output until the final layer, layer 5, which is sort of weird. And we also trained another transformer, this time with 4 attention heads, on strongly connected graphs instead of trees. And we find similar patterns to the backtracking patterns in this transformer, even though there's more attention heads. So we can see that these 3 attention heads, one in layer 0, one in layer 1, and one in layer 2, also have this like line thing. which is the backtracking process. And we find that some of the other heads in this transformer seem to be doing other things, which might also be aiding the backtracking. But it seems that like there's still like this one attention head where the backtracking is clearly happening. And we didn't have time to do activation patching on this. But yeah. Also, I guess the next step for this project would probably be to find similar circuits in language models. And I have a sort of hypothesis that training a language model to resolve like first order logic queries given a bunch of facts might also create this backtracking pattern in some of the heads. So I guess that's what we're currently doing, training transformers to like resolve first order logic and see if they actually form attention heads where they backtrack, and they're trying to see which facts lead to the goal that we're trying to prove. So yeah. Victor, did you want to say anything?
Yeah, not really. Just that there is a bunch of things we still don't understand about this model, like that we probably also will look into. Like it pays attention to, like there's some point where it pays attention to the commas. I don't know if that does anything. There is also like I think I'm not sure. There's one thing to comment is the part where its edge is backtracking. Like it seems like each edge is retrieving information from like on the first layer, retrieving like on the layer 1, it's retrieving information from the previous edge that leads to that edge, and in the next layer is previewing this two, like each edge is doing this kind of same backtracking to the previous edge, and that seems like it maybe. But the changing that doesn't seem to change the result that much, so I'm not sure how important that is. I think part of what I want to try, like maybe this week later, is to try removing parts of the attention pattern and see what happens. To see if the things we're not sure what they do are actually important, or some weird artifact from maybe a previous version, like a previous point of the training that and then it got overwritten with this better circuit or something. I don't know.
Awesome. Yeah, awesome. Great work. That was the 7 minutes at least. All right, does anyone have questions? Of course. Thank you very much. A little applause is in order. Does anyone have questions? I think I've muted you, Yoshi, because there's quite a lot of background noise. So just write in the chat if you want to say anything. Otherwise, I'm curious, how do you see this? So you have backtracking, you have some sort of like counterfactual planning-ish, who knows? How do you see this being a toy task for misgeneralization or for like misoptimization? And can you see steps towards it? Or is it just, okay, let's try this on and see if it's a general phenomenon with the backtracking on logical items of language models or something like this first?
Yeah, the sort of way that I imagined it is like, I imagine the way that we actually plan in language models would be to like use chain of thought, where we ask them to generate a bunch of facts and then we ask them to use those facts to prove something. And so I imagine that in like that sort of setting, these backtracking heads would be really useful to learn. So I mean, if that's like the sort of Mesa optimization happening within these models, then I feel like it's pretty important to understand the sort of like counterfactual backtracking phenomenon, or at least even to like disprove like the naive stochastic parrots perspective, where you just believe that language models have just basically memorized the internet and they're not actually really doing any planning or whatnot. Yeah.
I also think like I'm think about this. I'm kind of confused about what planning really is and what kind of things count as planning, and I think we should probably think like it seems like maybe there are other it's possible there are better toy tasks that capture like more general version of planning that we'll have to think about, but probably started with simpler ones like this. It's easier, and it's better to start simple and don't overcomplicate things because and basically I'm not very convinced that the kind of things we care about are clearly captured by this kind of by specifically traversing graphs in this way, but like it feels like there is a like realistic planning has some steps of abstraction that are not really captured by this. I mean, I think that realistic planning is going to be equivalent to always to some task on a graph, but it can be extremely big graph. I mean, that personally might not make sense. And maybe a better realistic model would be something like, I don't know, something where you have some information in each node of the graph, and there is some actual structure there that you can exploit. But yeah, I don't know. I think we need to do more research in that line to and think more about more philosophical links, like things like what planning even means and things like that.
Yeah, I guess when you begin putting information into the nodes, you end up having stuff like just like grid worlds or like Machiavelli that like are similar in structure.
I mean, a grid world is still like. I mean, yeah, it just depends on the observation. You can always see it as some graph, but I don't know.
Everything is a graph, right?
Also, the next task that we're training these models on, this chain of thought task, is sort of like where each of these nodes have some properties and we want to like, get the model to like propagate these properties to all of its children and it's like all of its descendants. So I mean, I guess if it learns backtracking that sort of thing too, then there might be some evidence that this is how at least some of the chain of thought in actual in GPT-4 might be done. So yeah.
Yeah, that's very
something to say is that you don't necessarily need n layers to backtrack n steps. You can do backtracking in parallel on multiple layers, and that seems like it stacks to probably stacks exponentially. We haven't tested that much. If the model, I think it did. I think we haven't tried it. Yeah, there's a bit of extrapolate. It works from bigger sizes. We haven't tried very much how big you can make the graph and have the models work. But yeah.
It'd be cool to like derive like upper bounds in the planning depth of like the model, given like the number of layers. But yeah, I guess that's the next step.
Awesome. All right. Thank you very much. Wonderful project. Excited to see the next steps that you've already outlined. So thank you very much. All right, Gian, number one spot here. We are ready for you if you are ready for us. And Gian,
great. Can you see my screen?
Yes, we should be able to. We cannot see your camera if you have that on.
Sorry, I'm in an environment that cannot turn on my camera.
Yes, that's right.
So, right. Yeah, sorry about that. So, wonderful. So let's start. Okay. So yeah, here I'm very delighted to be selected as one of the 4 talks. And today I want to present my hackathon project on relating induction heads in transformers to temporal context model in human free recall. Mechanistic interpretability seems to understand computations performed by artificial neural networks, especially nowadays transformer-generated models. People have found that there are large, important types attention head called induction heads, which they already know that such induction heads can emerge during an early phase change-like period during training. They have been proved to be very fundamental in the acquisition of the in-context learning ability of large language models. The basic function of the computation type, the basic function of the induction heads is to complete the sequence. For example, here's the random tokens in the sequence that are presented to the transformer, and it is presented as a node instruction. And so there are series of words like say, A, B, D, different tokens and many other tokens. And at the second time, when the transformer sees the same token node, which is marked as A prime here, the attention head will look back into the previous appearance of the token and attend to the next token just near the A token. So in order to complete the sequence, it will predict increase the output probability of the next token B. People already know that there are different computation types. One is called K computation, which includes the first layer previous token head and the second layer induction head. In another type, which is the rarer one, it is called the Q computation. And in this computation type, the first layer, it is a duplicate token head, which will look for the previous occurrence of the same token. Like so, if it at A prime, it will look back into the A, and then the output of this duplicate token head will be the position of the previous occurrence of A, and then the second layer induction head will use this information as a query in order to extract the location, the semantic information at the next token. Therefore, this attention head will output B. So that's basically the composition of the first layer duplicated token head and second layer induction head. However, less is known about how these attention heads can attend to nearby tokens, not only the immediately following token B. From another line, people have proposed many models about hippocampus. One well-known model is called the Tomac machine model. The same author have already related this Tomac machine model with the transformers, and we can find that there's a very similar structure between this transformer with causal attention and the TM model. When they trained the models on the spatial navigation task, they found that surprisingly, the softmax attention pattern in the transformer mimics the well-known place cell representations observed in the brain. However, little is known about the relationship between the general hippocampal recall memory and these transformer circuits. That's the reason why I look into the free recall task. In such a free recall task, the human subject is presented with a sequential list of words for them to study. For example, you can present to the subject light, cat, table, water during the study phase, so the human subject need to memorize these words. And during the free recall task, they are asked to record the previously studied words in any order. For example, it just record a word cat. Surprisingly, even though this task did not require the human to record the previous studied words in the specific temporal ordering, their recall indeed always reflects the temporal structure of the previously studied list. For example, because this time the human just record cat, so in the next time there will be very large probability of record the next word B. So that would be the table here. People typically have found that there are several effects that are very robustly observed in this experiment. The first is the temporal contiguity effect. That means the nearby words, like the C, B, D, these words nearby A, has a larger probability to be recorded compared with faraway words. The second is the asymmetric effect, where the following words, like the B, D, will have a larger probability to be recorded than the previous words. In one paper, they have commented that the TCM is the only published model that can naturally account for this different type of effect observed in human free recall memory. Now I will show you how we can directly relate the TCM model proposed in the past to the two-layer attention-only transformer models with the induction head. So sorry if I say anything unclear here, and I recommend you to look into the technical report about my project. So the word vector in TCM will correspond to the token embedding here, and the context vector in TCM will correspond to the position embedding. The pair of these two vectors will be the residual string observed in the typical transformer models. The first memory matrix is called the item to context memory matrix. It serves the role as a duplicate token head, and the duplicate token head will write the position information about the previous occurrence of the same word into the residual string, such that the context vector tj is updated from the previous one into the current one, tj. Then the tj will be used as a query into the second layer memory matrix called the context to item memory matrix, and the output of it will be the retrieved memory. That would be a combination of the previously stored memory item. During the recall phase, when you present the recalled memory, then the recall memory will pass through some embedding layer that is very similar to by comparing the recalled memory and the previously stored words, and that will give us a record word. Importantly, in this memory matrix, they are updated by the auto product between the keys and the values. Therefore, the whole stuff, indeed, we show that the TCM model is very similar to the Q composition induction head. There are also several other differences which I will not go into detail here. But basically, the position embeddings in TCM is recurrently updated by the for the position embeddings in the TCM model, but not in the typical formulations of the transformer model. Then, finally, I look into the empirical findings in the GPT-2 small model. I designed a prompt that consists of 2 repeats of the same sequence. Each sequence consists of 100 common words. I looking into the induction heads with the largest induction head matching scores, which is the code from the transformer length, and I calculated the similar attention patterns for this induction head. And now we can find that this attention patterns is very similar to the observed conditional response probability in the human behavior, except that the lag equals 1 is not usually plotted out in the human experiment. But in general, you can find that the shape is very similar between these two, so I call these CRP-like features. And later, I did a scan over all the attention heads, in all layers. And I found that for the early layers, between 0 to the 4th layers, there's no induction head and there's no CRP-like features. When looking into later layers, from layer 5 to the final layers, I found that all the induction heads will have these CRP-like features, like these patterns, and like these patterns. So they are all CRP-like. I also found that there are several non-induction heads that have CRP-like features, like this head L5H8, which is somewhat similar to the CRP-like pattern, but it does not have a non-zero induction head matching scores. So to conclude, I already connect theoretically and empirically between the induction heads and the human recall phenomena, and the TCM model used to explain such phenomena. These results will implicate that we might have a better characterization about the induction heads, and hopefully it can potentially increase the safety of the transform models if we dig this deeper and try to understand the relation between hippocampus models and the transform models. For another side, it can also point out to the fundamental role of human memory in learning. And for the future, I want to better characterize the competition types and study how these different competition types act on the CRP-like features and how these CRP-like features emerge mechanistically. So that will be the end of it, and I want to acknowledge the Hackathon event, the several transformer circuit and the circuit thread, and also the wonderful resources from Neonanda.
Nice. Thank you so much, Gian. What a wonderful project. Nice. And congratulations on the #1 spot there.
Thank you so much.
Do we have any questions from the audience?
Yes, I'd like to ask a question, if that's okay.
Yep.
Thank you so much for the presentation and for doing this work. It was really interesting. If you go back to, I believe it was slide 5. I wasn't quite sure here. So I've actually been doing some work with like human attention and model attention. Typically in cognitive science, when they're looking at human attention, they have some sort of eye trackers to see how their eyes shift as they go across context. So the thing that is not clear to me, so the phenomena that you're showing here is known as the in-context learning, right? So if you see A, B, B, T, and then you see A prime, then you're going to predict B prime because that's what you've learned, that this A prime follows, if you see A prime, then it must follow by B. Now, in the context of the recall, so when you see cut, are you supposed to predictable, or I don't quite understand what, like, I don't understand the graphs that well.
Yeah, sorry,
Could you-
I'm not clear about the task paradigm in human free recall. So basically, this is very different from the attention pattern of the eye trackers in human experiment. Assume that you just look at the screen, and the screen first shows the word light, and then it change to cat, and then change to table. So at each time point, you can only see one word. So
And
that's
the goal is so. What's the task for the human recall here?
so there's two phases. In the first phase is study phase. You only present with one word at one time, and we'll present you maybe 20 words or 50 words, and your job is to recall the previously studied word in any order.
Okay, and can you explain this this graph?
This graph means, for example, when doing the free recall task, there are one human that records the word cat. It is not required to record the next following word table. So this is not required in the task, and the human just prompt to record the previous studied word in any order. So here, the leg 0 corresponding to location for the cat, leg 0, and the leg 1 corresponding to the location for the table. So this results is about human behavior, and that means if at the current time point the subject record cat, it will have a larger probability record table, and a smaller probability record light, and a smaller probability record water.
I see. Okay, thank you.
And Abe, did you have a question as well? And I hope I'm not mispronouncing your name, by the way.
Yeah, I was wondering if you had like any sort of thoughts on like how like the induction heads would implement this sort of asymmetry effect. So I mean, is there like some sort of thing that they're learning that allows them to like discount things that are further away versus things that are closer, or?
I'm not entirely sure about the mechanistic about the composition, the CRP-like behavior. So I'm not entirely sure about how this behavior indeed emerge in the transformer models. So what we all know is about the K composition and Q composition. And in these composition types, only the previous token is stored into the current residual stream. So I'm not entirely sure about how they implemented this. My current guess is for the Q composition, when we calculate in the Q composition, in the second layer induction head, the previous idea is that they calculate the inner product between the similarity between the stored position of B and rotated version of which is stored in A prime. So this will require some kind of pointer arithmetic. Basically, you will need to rotate the position information stored in the residual stream. And my guess is that it will have some non-zero overlap between other positions. But there could also be other mechanisms that give rise to this type of behavior.
And you said that like the model that you tested this on was like an attention-only model, or?
So the TCM model, I directly mapped it to an attention-only model, but for the model I studied here, it will be GPT-2.
Oh, okay.
Nice, wonderful. And I guess one question for me is, I'm curious where you see this sort of work going, or what the broader implications of it are. So cognitive models are of course extremely interesting, and seeing, oh, this sort of behavior that we see in humans actually arises in transformers. Wow, that's very interesting. But what can we use it for? Do you have any thoughts here, especially for AI safety specifically?
I only have very general ideas, because for me, the first time when I read the connections between the so-called hippocampal TEM model, and I saw how it can be connected to transformers, I feel fascinated, and that's the only work that try to link the hippocampus to the transformer model. So that's why I look into the different formulations of transformers and say how it can inform our understanding about hippocampal memory. So later on, I just noticed the similarity between the induction heads in the hippocampal memory and how the behavior related to the induction heads. So for me, I feel like I still need to dig into the deeper about the details about these formulas, how we can transform the formulas from one side to another side, and maybe, for example, this already tells us about some characterizations about the induction heads, and I think maybe we can look into how this general phenomena can emerge during training and how the different combinations between the previous layer heads and the later layer heads, and this might provide with a clearer idea about how these different heads composite with each other. And from another side, I think it also can inform us how in the human memory modeling, how we can link the artificial neural networks about the cortex and link them to the hippocampal memories. So that will be the interaction between our current working memory and the hippocampal memory. And I think the transformer models like this would also shed light on that line of research.
Nice, wonderful. And yeah, I guess also highlighting that transformers seem to actually do some sort of computation that isn't just memorization, apropos the backtracking models, right? That like, oh, well, this is what humans do as well, apparently. And then, I mean, then we'll see if it's mechanistically the same. So, do we have any other?
Can I?
Yeah. Go ahead.
Sorry. This work is like super interesting, so I have many comments if it's okay. But I'm just going to take only a few more minutes. I know people like Ben Kim, who has been also very interested by the links between interpretability and neuroscience and psychology, has been trying to study whether allowing like human chess and Go expert top 100 players to interact with, let's say, advanced models, for the sake of argument, transformers, to see if they can learn behaviors or moves that will enable them to perform even better. Do you see any connections between this type of work and how it might help humans make decisions like more accurately, or to put it in the context of safety, can humans use this technique to predict model behavior as to prevent undesired behaviors from happening before they happen?
Sorry, maybe I'm not very familiar with that line of work. Could you just say it again about what is that did in that work?
Sure. So one thing that you can think about is the move 57 in the Go paper, right? The famous Go paper where all the non-expert humans, or even the expert human who the AI was playing with, like, oh wow, like we have never seen this. This is so unusual. Why is this happening, right? So maybe, in fact, there are a lot of moves like the move 47 or 57, whatever it was, such that it's not informative to us as average humans in the community, but it might be informative to an expert in the same way that some of these graphs or these formulas may not be very informative to an ordinary person, but it might be informative to someone who has been thinking about this for a while. So she's trying to understand how much model interaction with humans can help make the decision makings better, in the sense that are we better off by interacting with these models to make decisions? The work that I've been doing is I've been trying to see whether attention patterns can help humans predict model behavior. So I was wondering if you see any sort of synergies between these two lines of work.
That sounds a very interesting study. And I think in human cognition, people typically consider, we just mentioned the attention patterns of human eyes. So that would be one part. So currently, I did not find a direct relation between the phenomena I found and the study just described. But for me, it feels like for the human expert, and maybe there might be some objective for this human subject when they try to predict what is happening now and what is happening next. So that can be recast as a sequential prediction problem. I think that's somewhat similar to the transformer objectives. And but I'm not entirely sure about how the attention patterns observed in human expert can relate it to the recall memory I'm working here. Maybe there's some very deeper connections I need to understand.
Nice. Wonderful. All right, we'll take that as the last question. Thank you so much, Gia. That was wonderful.